It is my pleasure to introduce John Maria, who is a postdoctoral research fellow in computational sociology and criminology at the University of Trento, Italy. In 2020, he earned a PhD in criminology from Catholic University in Milan, Italy. From 2016 to 19, he worked as a researcher at Transcrime, the Joint Research Center on Transnational Crime of Catholic University, University of Bologna, and University of Perugia. In 2018, he was also a visiting research scholar in the School of Computer Science at Carnegie Mellon University. His research addresses the development and application of computational methods, especially machine learning and complex networks, to the study of criminal and social phenomena with a specific focus on organized crime, violence, and terrorism. So John, over to you, and you will find a lot of interesting folks in the team today just to listen to your talk. And I would also request everyone to please stay muted. If you have a question, please use the chat feature and I will be moderating the chat. And if you have any pressing questions, we can ask our speaker. Over to you, John. Thank you again.
So thank you very much for inviting me, first of all. Thank you for joining. I'm happy that there's both representative from the terrorism side as well as the computer science, information science side. So very excited to give this talk. Can I share the screen? Am I allowed to?
Yes, please go ahead.
Okay. All right. So you should see the presentation slide, correct?
Yes, we do.
All right, perfect. So this is going to be the title: Complex Network Artificial Intelligence and the Computational Study of Terrorism. A lot of topics. I'll try to keep it as brief as possible. I'm not very good at timing, so please needn't stop me or give me heads up if things are running out of time. So who am I? This is a rather philosophical question. I wanted to keep it as material as possible, and Nathan actually anticipated me, so I will skip it. I'm just a postdoctoral research fellow now at University of Trento in Italy, and computational sociology and criminology. And as he said, I'm mostly interested in terrorism, organized crime, and urban crime, especially violent crime, through the application and development of machine learning and complex networks and graph learning and causal inference methods. So the talk outline will be structured in 4 different kind of sections. First one will be a very short overview on computational modeling terrorism research. And then I'll present 2 studies that I co-authored that are actually on this field. And then I'll try to wrap it up with some concluding remarks, hopefully stimulating some discussion at the end. Especially given the heterogeneity of the audience present here today. So before starting, I just wanted to thank 3 of the 3 co-authors that really made it possible to publish studies and to write and to develop the studies. So first of all, Professor Kathleen Carley at Carnegie Mellon, and then Dr. Igor Kirkchenk, who's, I think now he moved from Carnegie Mellon to be at the West Point Academy. And then Dr. Mihailo Bartulovic recently awarded a PhD in computer science at Carnegie Mellon, now working as a software engineer in the startup that Professor Kathleen Carley founded. So a very short overview on computational modeling terrorism research. Since the 70s, there have been appeals about the state of empirical research in terrorism, and many scholars over time try to highlight the various methodological issues that terrorism research, the empirical side of terrorism research had. These are mainly 4. So we have a lack of good empirically grounded research, so most literature reviews and opinion pieces, theoretical pieces without any kind of empirical backup. The over-reliance on secondary sources, which made it very difficult to innovate information-wise. The low level of collaboration among scholars. Terrorism studies are really spread out across different fields like economics, political science, security studies, criminology, now even information science and computer science, and there's very little effort to collaborate among scholars and across fields, and then the high amount of one-time contributors. So people that contingent on the particular public pressure to study terrorism move from one field to terrorism studies just to publish a study and then move to another field because the public pressure and the academic pressure is in another focus on another topic. So in 2014, Mark Sageman talked about this problem of stagnation of terrorism research, especially in light of the massive fundings that after 9/11 were allocated to the field that actually was not able to fulfill the many problems and respond to the many open questions about terrorism that are still open. A newest review published in 2020 by Bart Sherman actually was a little bit more optimistic, and he pointed out that we are moving towards the solution of some of the long-standing issues, although some are still in place to date. Economics and political science, among the many fields that really deal with terrorism, are the ones with the highest methodological standard, which is not a surprise. This is kind of common for many social phenomena and social problems. And in the last 10 years, we have two areas in quantitative and computational social research that fostered a lot of research, a lot of interest in terrorism research. These two are network science and machine learning and predictive modeling. So the unbearable lightness of terrorist networks. Why do I call it unbearable lightness? Because we have this spike in interest in terrorism from the point of view of social network analysis, a lot of studies. However, most applications really rely on affiliation networks or alliance and rivalries networks, which are mostly characterized by cross-sectionality and blurred temporal boundaries, unidimensional depth, no multimodality, no multiplexity. So basic networks that kind of map communication among affiliates or co-offending, but nothing deeper than that. And generally, these kind of applications are mostly mapping physical connections between individuals rather than more abstract but still meaningful link in the study of terrorism. And then from the machine learning and terrorism research, a lot of optimism. Machine learning fostered that in a lot of fields, increasing data availability, mostly thanks to the efforts at the Global Terrorism Database folks, University of Maryland and START Center. Attracted scholar from known social science field for applying to apply machine learning and predictive modeling. However, after a lot of works that came out as vibrant debate that models are not able to meaningfully forecast, for example, violence eruptions. This was a kind of a critique that came out from the conflict research agenda that is really relevant also to terrorism research to date. So the machine learning hype brought more excitement at actual results, possible causes, the inability to capture complex interdependencies between events, the lack of causal knowledge and theoretical reasoning. Data are still too scarce in spite of the many efforts that have been done, and the insufficient spatial temporal resolution, which makes it very difficult to predict such a rare and high impact phenomenon. So this talk, in the spirit of what I just said, this talk will try to present two works that hopefully goes in the direction of tackling some of the problems that I mentioned. So the first one is learning future terrorist target through temporal metagraphs, which aims at forecasting future targets, leveraging the ability of graphs to capture richer operational dependencies across events, and then multimodal networks reveal patterns of operational similarity of terrorist groups, basically present a graph representation learning approach to detect behavioral similarity between groups at the global level. So here's the connection between the content of this talk and the title, which is the integration of complex network artificial intelligence for the study of terrorism. So the first study, we have three issues with the extant literature on terrorism. Operational information about terrorists are studies at overly aggregate temporal levels. So like years or months or quarters, which makes it very difficult to have an utility at a policy level. Micro level forecasting only focusing on events and lethality to discriminate between events, and this overlooks the heterogeneity of attack characteristics. And then computational attempts mostly ignore theory, applying the let the data speak philosophy. So the aims of the work are to develop a forecasting modeling framework to predict target at highest risk of being hit by operating at fine-grained and temporal level, exploiting richness of data in terms of event characteristics, and building upon theory. In fact, the theoretical premises here, so strategic theories of terrorism originated in the study of conflicts by Schelling, seminal works in 1980. So terrorists, we can say that it can adapt and act in adaptive and adversarial setting. So the strategic frame, which was mostly framed by McCormick, assumes that they operate within some sort of collective rationality. So we can think of groups as a single entity that makes decision, and the strategic decision making is limited by several constraints that influence the type of attacks that a group or an actor will plot. It means that there are some characteristics, some factors, some variables that impact and influence the way in which these events will occur and the kind of nature of these events. Also, terrorism does not occur at random. We know that it follows specific patterns like self-excitability, self-propagation, and spatial concentration. This is well known, originated from the literature on crime concentration and violence concentration. So the point is, what if regularities, besides the spatial temporal component, also exist in terms of event characteristics? So this is the main, like the supreme question that we try to target. And the second question was, okay, but then how can we integrate, if this is true and if we want to investigate it, how can we integrate the two fundamental layers, the temporal dependence and the operational dependence of strategic decision making? This graph kind of summarize it. We think that the solution is temporal method graphs. So temporal method graphs are able to capture connections over time between events, but also across event characteristics. So we move from IID research design that are very common, in which events are actually considered as independent of one another. We move to a more kind of a sophisticated way, which is thinking about temporal dependence. So one event will impact the probability that another event will occur. And we go to the temporal method graph approach. Basically, we know there's a temporal dependence, but we also want to investigate whether there's a value in understanding the interdependencies between event characteristics. So the fact that maybe some event has some characteristic will impact the probability that some similar events will occur in the future. So we focus on two countries, Afghanistan and Iraq, for the sake of numerosity of events, but also because they're quite different countries. Even though they are high frequency countries where terrorism was very prevalent. But if we see the data down here, we see that we have different temporal distributions, we have different quantitative considerations to make about these two countries. We have different ecological and contextual characteristics that are linked to these two countries. So Afghanistan mostly related to the activity of Taliban, while Iraq from 2001 to 2010 saw the presence of many different groups. So we thought that were two interesting, let's say, settings to test our framework. So the analytical pipeline here, I try to summarize it, but we basically focus on each attacks, deploy tactics, utilize weapons, and attack targets as distinct dimensions. Tactics in the global terrorism database are originally labeled as attack type. And by focusing on this free dimension, we derive multivariate 2-day base time series from 2001 to 2018, in which each time series observation maps the centrality of a certain feature in its dimension in a given unit. So basically, the centrality of that particular tactics or that particular weapon or that particular target, it is actually capturing how popular, how used, how prevalent that particular tactic, weapon, or target was in that particular time frame, which is again a 2-day based unit. And then we forecast the most central future targets, trying to learn the patterns of association in previous time steps between tactics, weapons, and targets. So we try to infer what will be the next target by using information on past attacks and on this past centrality values that are a byproduct of the network representation of connections between the different event characteristics. And we also test with different input weights. The algorithms are tested with different input weights because we wanted to know how long should we go back in the history of the attacks to try to optimize predictive accuracy. The longer we go And it means that the more stable the activity of a group of a certain terrorist activity is, the shorter the time frame, the highest is the frequency with which the actors that are active in that particular context are changing their actions. And we experiment with different machine learning and deep learning approaches, but we also compare between matter graph time series. So this idea that by combining the temporal and event characteristics networks and resulting graphs, we can gain more knowledge, with shallow time series, which just use the count of features in each time unit. And we wanted to understand whether, using our approach actually allowed us to optimize our predictive accuracy. So this is just a graphical representation of how we started the whole project, by representing, starting from our tensor representation, in which we have our days and our matrices with our days and with our event characteristics and the count of each characteristic for each day, which are divided by dimensions. So we have targets, we have tactics, and we have weapons. And from that, we derive our networks, and then we calculate our centralities as a byproduct of prevalence for each of the event features that we wanted to study. We tested different algorithmic architectures. So baseline, basically, we wanted to forecast centralities at t+1 are the ground truth at time t. So basically, it's assumed that there's no change. What was most central in the past, it's going to be central also in the future. And then feed-forward neural network, simple class of neural net, designed for sequence data. We wanted to test whether we have a temporal structure. And then 4 different algorithms that actually bear a temporal and a sequence structure. So LSTM, CNN with a 1D convolutional filter, and then bidirectional LSTM. So basically it's an expansion of LSTM. We learn the sequence forward and backwards, and then a combination of CNN and LSTM. So we stack together a 1D convolutional layer, a dense one, and then an LSTM and another dense. For performance evaluation, basically the centralities are in continuous values. So from 0 to 1, we normalize them, but we're not really interested in, so the algorithms actually learn the centrality value, but we're not really interested in understanding how well they were predicting the actual continuous value. So we transformed the problem from a regression one to a ranking one. So basically we developed 2 different measures of accuracy, element-wise accuracy, which basically tells us, is the model able to forecast at least one of the 2 most central ground truth targets for each time unit? It's a little trivial. So we wanted to know whether among the 2 most central, the algorithm is able to pick at least one. And then we have set-wise accuracy. So we wanted to understand whether the model was able to correctly forecast the whole 2-item set. So we have 2 ground truth, most central targets. We want to understand whether our algorithm is actually able to predict those 2 correctly. So the results, comparing architecture and models, we have Afghanistan on the left and Iraq on the right. We have the blue dots are the method graph algorithms, and the lighter, let's say cyan ones are the ones with the shallow time series. What emerges is that generally the metagraph approach is far better in predicting the next future targets. This means that our network representation actually allow us to have much more information about what's going on in those 2 settings. We have variation in terms of the ability of the algorithm and the input width for each of the 2 settings. So the first result again is that graph theory time series outperforms shallow time series in forecasting because we have a richer representation. Second is that bidirectional LSTM in both settings have the highest performance, although with different input widths, means that basically the fact that we are letting our networks to learn the sequence backwards and forward allow the algorithm to understand a little bit more of the context that is surrounding our information. And this actually, we see that this gain much more predictive accuracy compared to other approaches. And then the third result is that Afghanistan has the highest set-wise accuracy in the BIL-SDM experiment with 30 units as input width. So meaning that in Afghanistan, we have more stability, which makes sense because Afghanistan, again, is populated by less terrorist actors. While in Iraq, the highest set-wise accuracy is lower. And also we have an input width of 5, so 10 days, basically less regularities. And the fact that the result is less, let's say, optimal means that we have more actors, and that these more actors are also innovating more in the country. So this makes it a little tricky for the algorithm to learn. For the batch configuration, just to focus here, what we see is that on the blue, we have the ground truth. So the number of times that each of these targets were among the two most central in each time unit. And then we have the predicted in green. What we see is that the algorithm is very good in picking up the two most prevalent, while it struggles a bit to pick some of the less prevalent ones, which is something that we should and we want to work on. Of course, when this kind of complexity and heterogeneity and the phenomenon is linked to the fact that we don't have so much data, especially because we're transforming this in time series, it's going to be challenging. Probably some data augmentation technique will help, and we'll certainly think it through. And if you have any suggestion at the end, I'll be glad to hear. So conclusions for this first study: temporal method graphs provide richer context compared to shallow time series, in line with theoretical premises and our assumptions and our hypotheses. Then the relevance of model testing using different amount of data. So the behaviors show different patterns in different countries and contexts. So there's no one size fits all solution. And then the promising approach in context with high frequency terrorism. However, limitation: we lack a distinction of different groups and actors operating in the same country. So the hierarchy scenario is problematic for that precise reason. And then we don't embed geospatial information, which probably might help us getting more information and maybe refine our prediction. And the current engineered system does not capture rare events. So 9/11 and similar events gets lost. We have still to figure out how to solve the black swan problem. So this is a reference. It was a study published in 2021 in Nature Scientific Reports. It's open access, so if you want to look it up, it's there. Second study: multimodal networks reveal patterns of operational similarity of terrorist groups. So basically, again, the idea is to try to combine machine learning or graph learning with network science and complex networks to try to reveal something about how terrorism works. This is not a predictive study; it's more of a kind of a descriptive inferential one. So the combination of weapons and targets constitutes a group operating profile, and the choice of targets and weapons is constrained by a number of factors like material resources, support, goals, ideology. So represent actors in the operational profiles through graphs to detect behavioral similarity is the actual aim of the study. And it's important to be able to discriminate in the study the heterogeneity of groups while looking at weapons and targets, because weapons and targets and the tactics that they use are the actual most concrete characteristics that lead to attacks in the end, and to understand the impact on human lives, but also the economy and political stability of attacks. Surprisingly, also, we weren't able to find any comparative account of heterogeneity among terrorist groups and terrorist actors in a global scenario, which means that we lack understanding of how similar groups are, how different they are, how they operate, do they innovate, do they change over time. So we use, again, the global terrorism database, and we consider terrorist actors that have plotted at least 50 attacks at the global level from 1997 to 2018, accounting for a total of 105 groups and more than 42,000 events. And again, we focus on tactics, targets, and weapons. Here we have a visual representation of, first of all, the number of groups and their number of attacks. We see that most groups are actually around 50 to 100 attacks, and we have a small number of outliers, which are mostly Islamist actors that were able to plot thousands and thousands of attacks in this time period. We have also the data about years active, which we see that it's pretty rich as representation. We have groups that have been active with high frequency, but just for a little amount of time, and then groups that have been active for even more than 20 years for all the time period under consideration. And we also have the disaggregation of groups by their ideologies. See that Islamism and jihadism is the most frequent one, and then also we have ethno-nationalist groups as the second most frequent. So computational methodology. What we did here for each year, we took this multi-model network framework in which basically we had 3 different matrices, again, for each year. And each matrix was a group by tactic, group by target, and group by weapon matrix, where the link were weighted links, meaning that the weight was the number of times that particular group was used that particular tactic or target or weapon in that particular year. So by starting from this scenario, basically we transformed this multimodal framework, which is a multimodal bipartite framework, into a multimodal unimodal framework by using our reducible graph procedure. So basically, in the end, we come up with networks that connect groups, and that connect groups if they were similar in the use of tactics, targets, and weapons in that precise year. And then we devised this multi-view modularity clustering procedure that was first developed by Ian Cruikshank in his doctoral thesis, which allow us to optimize this measure of modularity across different modes of the networks. And we do this 2 times. So basically the first multi-view modularity clustering computation is allow us to filter out the cluster 2 outliers. So basically we filter out those organizations that in each of the modes for each year are particularly impressive in the way and different from the others in the way that they behaved. And then we reiterate the procedure on the refining cluster separation because we wanted to also disaggregate the critical mass of groups that quantitatively seemed more similar, but were characterized by much more nuances in the way in which they were, for example, combining some tactics with some targets and weapons. So, for example, these are the reducible graphs for 97, 205, 211, and 2018 for all the 3 modes. And we see that we have outliers, which are basically isolates, and then we have a core component of groups that seem very similar because they're very connected. But in the end, if we look at the nuances of the data and the distribution of the weights in each of these networks, we see that there's still something to be discovered there and still heterogeneity. And that's why we wanted to run a second attempt for separating and refining the clusters. So we detect some clusters in the end. Again, the fact that we use this multimodal based modularity allowed us to end up with having clusters that combine together the data on tactics, targets, and weapons. And we see that the number of clusters doesn't seem to give us or provide any relevant information. There's not a trend there. It seems pretty flat. But if we consider the number of active groups over time from 1997 to 2018, and then we calculate the ratio between the clusters and the number of groups, we see that actually we have a decreasing trend, meaning that probably this ratio cluster groups showing a downward trend probably is indicating us there's a reduction of heterogeneity and complexity at the global level. So we add more groups, but we have this kind of similar number of clusters over time. It means that we don't need more clusters to study and to link the increasing number of groups. So the increasing number of groups probably are groups that are more similar to the others, and we don't have different groups that are particularly heterogeneous. So we have a general sensation that probably heterogeneity and complexity is reducing at the global level over time. To try to understand this fact better, we also look at the stability of co-clustering. So we use the adjusted random index and the Folksmel score to different measures of how the clusters were stable over time. And what we see is that we have a strong stability from 2011 to 2018, meaning that group that had a certain behavioral pattern in 2009 kept it quite fixed in the following years. So they were clustered with similar groups, and those groups were not changing their behavior in this time frame. We also have a region of stability in the years 2002, 2006, meaning that, again, groups were generally clustered together in the past are going to be clustered together in the future, meaning that the two are maintaining their same kind of behavioral profile. However, before 2002, we have a high variance. So this is possibly due to new actors coming in or already active groups that are changing their operations significantly over time. And the fact that Group A and Group B were clustered together in 1998, it's not a guarantee that they're going to be clustered together in 1999. Actually, there's a very low probability they're going to be clustered together, meaning that at least one of the two switch their operation. It's going to be clustered with someone else. So our idea was also to understand what drives then called clustering. What are the drivers that made groups being clustered together in a year? Because this is a sort of a way to understand, again, what drives operational similarity. And we wanted to test some hypotheses that we had, because mostly in the literature, we had this separation between groups that is mostly based on their ideology or their geographical setting. But our intuition was that maybe if we look at operational characteristics and their behavioral profiles, we can see that maybe the fact that two groups are of the same ideology or do not have the same ideology doesn't mean much, and we can see some similarities at the behavioral level, even when two groups are fighting for two very different reasons. So we used exponential random graph models on the fully connected component-like networks derived from cluster. So basically, each group, it's going to be connected to all the other groups that are in the same cluster. These give rise to fully connected networks or isolates when we have groups that are just isolated in their own cluster. And we run this separate year-by-year models using exponential random graph modeling. So we look at sum of feature weights, like is the amount of resources activity a driver of co-clustering? And the answer is yes. As we see on the top left, sum of feature subplot, when the dots are blue, it means that the result is significant. And we see that, yes, the fact that two groups share the same amount of resources, so we're active in the same way to the same extent to another, that was a driver of co-clustering. The number of known zero features in the original networks is also is also a driver of co-clustering, and this is a repertoire of diversity. So the fact that two groups are very little diverse or very high diverse, the fact that two groups have these characteristics are correlated with the fact they're going to be clustered together. So if we have one group that it's not really diverse and another one that continues to differentiate their action, they're not going to be clustered together. However, the contrary holds true. So, if you are very not very innovative and not very diverse, you're going to be clustered with similar groups and actors. Now we also look at most common targets, most common tactic, and most common weapon. So the fact that you use the same weapon mostly, or you deploy the same tactic, or you go against the most common target, are these drivers of operational similarity overall? Not really much. We have some some years for which some of these are significant, but mostly we don't bear any statistical significance in understanding similarity as by proxy of sharing the same most common target, tactic, and weapon. And I think the most interesting too is that we also look at region and ideology. So are groups operating in the same region more similar? Not very much. So across the years, we have only 5 years in which this relation is actually significant. So this means that the fact that two groups are operating in the same scenario, like Eastern Europe or Western Africa or South America, doesn't mean that they have higher chances to be operationally similar. And the most interesting one to me is that the fact that ideology is not really a driver of operational similarity. So the fact that two groups are sharing the same ideology doesn't mean much. We might have, so the fact that, for example, two groups are jihadist groups, doesn't lead to a higher chance of being clustered together than one group that is a Christian one and one group that is a jihadist one. And this also holds true, for example, for groups that are left-wing and right-wing groups. So we have anarchist or communist groups that are very similar, for example, to racist and Nazi groups that are active in the time frame under analysis. So the conclusion of the second study, multimodal graphs allow to capture operational similarity across terrorist groups. And this again is a good fact that embedding together complex networks, and so the network representation of behaviors beyond physical representation of connections between groups is important to gain knowledge about how they operate. And then we detect a reduction in heterogeneity and variation in operational behaviors in the last years and a consequent higher degree of co-clustering stability over time. And then from the URGM results, we see that the yearly amount of resources, activity, and repertoire diversity drive co-clustering in different directions. And also the combined measure of the two is also a predictor. However, we see that sharing the same ideology and acting in the same region do not correlate with operational similarity. And we think that this goes against most of the public debate about terrorism that is currently heard on media and even in academic outlets. So this is a reference. This study was published in Terrorism and Political Violence in 2021, but you can also find it on archive with all the supplementary analysis as well, and all the robustness tests that we did. So before getting to the end, just some concluding remarks. So the computational wave in crime research, I come from criminology, so I see this from the lenses of a person that works as well works on terrorism as well as on crime. And since at least 2010, we have seen a diffusion of computational approaches for the study of crime and criminal behavior. And this also fostered interest in the public policy sphere, all the debates about around predictive policing and criminal justice risk assessment tools. Some factors I think were decisive in this increasing interest and attention on computational study and computational analysis of terrorism, of crime, the higher availability of data, the democratization of programming languages and statistical software, and the dramatic shift to quantitative measurement of crime, and also the demand for data-driven public decision, which also opened some business opportunities for academics and analysts that were working in the sphere. But what about terrorism? So terrorism research has certainly been lagging behind. The trend is similar to the one witnessed in crime research, though. So we see that there's an increasing interest, although with a slower pace, probably. And there's certainly an increasing fascination with computational methods, sparked by, especially by the opportunities offered by social media data availability. So Twitter, but also other social media channels have been kind of labeled as new El Dorado because of the ability to create original data that have been not been used before. But still, I think that there's still many structural problems that are mostly four. So the first one is the lack of integration and dialogue between disciplines. Again, terrorism researchers lack methodological expertise, while computer science and stats mostly lack the domain knowledge. And the fact that these two communities don't talk to each other is a real problem to me, because we will face the risk of investing much on one side, on the computer science side, to create sophisticated models, but without understanding the phenomenon under analysis. And on the other hand, terrorism scholars, criminologists have the domain knowledge, but do not have the tools to really apply what they know to create meaningful models for both research and policy. And then terrorism research is seen as playground. Again, the problem of one-timers following the hype for the AI for social good trend, that after the probably 2016, so after ISIS, when ISIS seemed to ended to be a problem for the Western world, people moved to other types of social phenomena, which are certainly important, like COVID, disinformation, fake news, polarization, but leaving a sort of a desert around a computational study of terrorism, probably until the next ISIS pops up, when attention will be again brought to the topic, and but this process really makes it difficult to create a homogeneous and a continuous research agenda that will survive in the future. And it really makes it easier just to follow short-term projects that are justified by funding and by the fact that we all have to publish and so on and so forth. But this won't help us having, the ability to create solid infrastructures and solid research communities. Then data scarcity beyond the GDD, which is again the best source and the one that I've been working with since my PhD. There's no easily accessible, comprehensive, reliable data set beyond this one, which is a problem. Another one is that there's a small integration between the offline and the online world. So folks working with the GDD are just working on the offline world, and then folks working with Twitter data are just working on their online world. They're not talking to each other. There's no integration. What I think there'd be certainly promises in trying to look how, for example, the offline world impact the online world and vice versa. And then, which is probably the most important one, most technical one, is the fact that we have a rare and balanced phenomenon here. So predictive modeling with crime relies on millions of observations, as millions of crime occur around the world every year, while recorded terrorism events luckily are just around 2,000, probably more now, as per GDD data from 1970 to today. So we're talking about a very different amount of information that we can rely upon for our studies and for our research. So thanks for your attention. I hope I was good with time this time. I think we're around 40 minutes. And if you have questions, I'll be happy to answer to them, or critiques or whatever we have to discuss. This is my email, by the way. So if you have to go and you want to drop me a line afterwards, my email is open, and I also have Twitter. So I'll be glad to hear from this talk on those channels as well. Yes. So that was it.
Thank you, John, very much. I'm sure this is a very, very interesting talk, and there must be several thoughts and questions. Let's open the floor for discussion, and I'm also monitoring the chat. So if you have any questions, you can also use the chat feature, but unmute yourself and go ahead with the question.
Hey, John. Question about, I guess, how you're calculating or how do you derive similarity? I think you kind of you mentioned it some in here, but as you go through and look at, I was trying to bring all this together, but when you talk about similarity in that, I forget which slide it was, but you were talking about co-clustering between targets, tactics, weapons, ideology. Yeah, how are you actually calculating? Okay.
Maybe this one or the previous one?
No, I think it was the one where you were showing, it was towards the end, what was driving co-clustering.
Oh, okay.
Yeah, but I was just curious, how are you calculating similarity? Because like this, you're showing here, I guess, co-clustering, but then prior to this, you've already derived that they were either similar or not similar. Is the network based on similarity?
Yeah, so thank you for your question. Of course, like I had to be very fast on some details, so it's totally fine if you. I mean, it was my fault. So the thing is, yeah. So the fact that two groups are in the same cluster is how we measure similarity. So the fact that two groups are in a cluster are by definition similar. Now, the fact that so what we wanted to study is, okay, let us see what are the variables that we didn't use in the original network representation that are correlated and that are drivers of the similarity. So at the beginning of our framework, what we do is we have this modal networks for each year and for all the three dimensions. So we have tactics, targets, and weapons. We have this group by type of tactics, group by type of weapon, group by type of target. networks that are bipartite networks, where the weights are actually the count of the instances. Like, I don't know, I'm ISIS and I use in 2015, I used 20 bombing, something like that. So you're going to have 20. So we have this weighted bipartite networks, which are modal again. And then we transform these bipartite networks using this radius ball graph, which is some sort, it's in computational geometry, is some sort of a nearest neighbor problem. So basically, we take these these bipartite networks and we transform them into group by group networks. And in that case, two groups are going to be connected together if they share a lot of the weights that were originally placed in the networks. So basically, if you want to think it more matrix-like, it's the most similar the rows of the bipartite networks are for two groups, the more likely that they're going to be connected in the unimodal network. Now, once we have those networks, we are going to run our clustering procedure, because the fact that two groups are going to be connected, it's not per se an assurance of similarity. There's maybe one group is connected to many other groups, but the connections have different weights. So we want to disentangle that, and we want to derive what are actually the strongest links to other groups. And that's how basically we then create the links. We then create the clusters by looking at the links of the unimodal networks. So basically, okay, yeah. So basically, we have our bipartite networks here, which are these ones, and then we convert them into monopartite, and we're going to have these ones here. These are the monopartite networks. We see that our outliers are not connected to anyone. These are the groups that are very outstanding. But then you have a critical mass of groups that seem to be very connected, and at the first glance, you might say they are similar. But actually, the weights of these connections are very different. So basically, the clustering procedure allows us to also extrapolate similarity between those critical masses. And then we have these clusters that actually optimize across the three different modes. And then when we have these clusters, what we do is, okay, now let's try to use variables that we actually didn't use. Some of them we actually use them, but some of them were actually embedded in the procedure, but some others were not. So we wanted to understand whether, okay, we have the sum of feature weights, probably it's going to be correlating, but in which direction? And then the same with number of non-zero features, in which direction as well. But then we wanted to understand whether what we derived, is it actually associated with, for example, the same ideology or the same region, or we can actually see that there's a operational similarity going on, operational similarity pattern going on also for groups that are very distant, very far away geographically, or very far away in their ideological spectrum. So I don't know if that answers the question, but there are multiple steps in the way in which the similarity is actually derived.
No, that is helpful. Yeah, and that's what I was wondering about. Yeah, so I mean, you are taking multiple steps to do that, and I guess when you get those kind of the monotype graphs, I guess partite graphs, are you measuring any kind of, I guess, I'm thinking something in terms of like clustering coefficient, modularity, something where you can kind of measure the intensity or the strength of that similarity?
Oh, well, that's a very good question. Actually, we also measure clustering coefficient, degree of sortativity, degree of centrality, and stuff like that. It's all in the paper. Okay. I didn't include the plots here. But we also look at that to see how over time, for example, the networks change. So we see more clustering over time, which is also another proxy of saying that probably there's more homogeneity going on over time. So if you look at check the paper, you'll see that okay. We also look at that. And if you have questions or curiosities, please send me an email. I'll be happy to answer to that. Thank you for your questions.
Thank you.
Thank you, John. I think we have another question from Brian. Please go ahead, Brian.
Yeah, thanks. This is great. I have a question about sort of, sorry, hold on a second, about the distribution of the data within the GTD and how that's impacting both papers, right? So we know that there are things like, I'm going to say 80% of all attacks fall into either they're either bombings or shootings or something like that, right? So there's a lot of very sort of, let's say, low fidelity buckets that these events sort themselves into, in terms, particularly, I think, of target types and weapons and tactics, to the extent that those are similar to each other, which seems to me like has some real potential impacts in both of these papers, right? Like in the predictive paper in the first half, it seems like I wonder to what extent you guys addressed sort of the like real naive models here, right? Like what happens if you just guess the most common outcomes here for some of these variables, right? Like if 80% of our attacks are bombing or shooting, then your results with a more sophisticated model are, I mean, what is the divergence from chance on those, right? And then similarly here, when we're talking about driving the co-clustering, this is a great slide, I think, to illustrate the point. Like, we're doing so much flattening of the nuance of what's happening from event to event in the source data that I'm actually really curious what happens when these methods are run on data that have far more specificity about what happened, right? Like, did you guys dig into sort of the weapon subtypes, the target subtypes, or even consider how this is different if you had actual textual representations of what was happening in ways that you could get much smaller, more specific measures of similarity between, you know, event A and event B?
Yeah, so thank you for the question. That is a great point. Actually, one of those points that actually kept me awake a lot of nights over the years. But so you're working at JDD, so you know that way better than me. The problem that you mentioned are there. One thing that I didn't mention before is that we use all the four possible weapons, 3 possible attack types, and 3 possible targets for each observation in both cases, both the predictive and you know, co-clustering stuff. So we didn't stop at just the primary one or the first column, which is something that unfortunately many people do it in this field. Sure. So that does that. I would say that for the predictive part, somehow the baseline algorithm that we tested, so basically just keeping the most, using the most common, the most central of the past time unit as the next one, that is a sort of a test for how the algorithm is good at picking just, you know, just the most common and the most frequent, rather than being able to really discriminate. And actually, the fact that the baseline approach doesn't provide us with very good result is a good way of saying that more sophisticated algorithms are actually able to pick up some of the complexity of the patterns in the data. Now, using the subtypes, I tested in the early days, and then I stopped that just because of the fact that, unfortunately, the number of observations here are not as many as you know, they don't allow us to go with a feature space that is gigantic. So we would run easily into the curse of dimensionality. So definitely that's a you know, that's a limitation of the study of the first study. For the second one, I see it less as a limitation, and I don't think that there will be a problem in testing the approach using subtypes, because in the end, we are using here a sample of groups that are pretty heterogeneous, even though we're talking about, you know, the majority of them are jihadists or ethno-nationalists, but they are jihadists and ethno-nationalists that have very different characteristics. So we have jihadist and ethno-nationalist groups that operate in different geographical contexts and with different resources again. So yes, you know, we have the usual suspects that generally use the same bombings and, you know, firearms and stuff like that. But we also see a lot of heterogeneity in general. for some groups that have some particular ideologies, like, I don't know, environmental and animalist groups, or far left groups and stuff like that. And then one way that is embedded in the system that prevent this kind of flattening. So flattening of the various characteristics is the fact that we use weights. So we just don't use the fact that that group use a firearm to carry out an attack, but we look also at how many times did you use that. And by using this multimodal framework, we also implicitly look at the connections, like how many times you use a firearm, but how many times you use a firearm against like a police officer, or how many times you use firearms against a civilian. So yes, if we look at the single modes and the single variables alone, you know, they might seem flat. And this is probably true mostly for the predictive paper. But still, we might have that concern also in the second one. But the precise objective of these papers was to try to combine and to try to represent a complexity of terrorist behaviors beyond a single source of information, which might be tactic, target, and weapons. So we wanted to have a representation that was able to capture interconnections, weighted interconnections that were taking into consideration, you know, the complex spectrum of combinations of behaviors, their frequency, and the heterogeneity coming out of that. So I agree with you that the optimal model would, especially in the predictive case, would pick up more nuanced variables like the subtypes and the sub targets and stuff like that. I think we have you have three levels of targets. I'm very afraid, and that was the first feeling that we had when we tested that with this numerosity, with this number of observation, that would end up being completely meaningless. So we figured, okay, it's better to have a model that is a little bit less rich, but meaningful, rather than having a structure, a data structure that is very rich, very nuanced, but that bring no result at all. So that was our kind of a trade-off in the decision on how to design the system, especially in the first paper. I don't know if that answers the question, but
yeah, no, that was great. Thank you.
Thank you.
Thank you, John. Thank you, Brian, for the question. I know that we have we are 4 minutes over the meeting time, and I see there's one hand up. But I would like to ask John, do you have a hard stop, or can you entertain another question?
No, please go ahead. Don't worry.
Oh, thank you so much. Heather, please go ahead with your question.
Sure. Thank you, Dr. Joseph. This was like, insightful. The findings are really insightful. I just had a question about this slide, exactly the results. What drives co-clustering? The first two things, like I wanted to ask you the amount of resources activity. What did you mean exactly by that? The amount of resources activity, and also the repertoire diversity. So yeah. Can you just explain on these two?
Sure. So when we constructed this variable, we looked at the original bipartite networks. So again, a model network in which we have, for tactics, weapons, and targets, we have for each year we have our groups, and then the tactics, weapons, targets, and we count the number of times that group particularly used firearms, or used bombings, or used whatever. So the first variable here is just the sum of feature weights. So basically we summed the number of weights for each group in each year and each mode.